In this problem, we have the following circuit diagram. We need to find the Norton equivalent circuit with respect to terminals A and B, and we also need to find the Thévenin impedance for it. So first thing I'm going to do is combine these two resistors because they are in series with each other. If they are across like this, we are allowed to combine them together. And if we combine them together, we are going to get 15 plus J times 30. Now we're going to focus on transforming this left side. We're going to use source transformations. More information about this linked in the notes below the like button, section 9.7. But we're going to turn our current and our impedance, which is a resistor, in parallel to a voltage and resistor in series. We can do this with the source transformation. We're not touching the right side of our part right now, only the left and middle part. So for here, we are going to have the resistor of our 15 plus J times 30. This part is not going to change. What is going to change is that we are going to have a resistor up here as well. And then we are going to have a voltage with a plus minus here, and this is our V. Now we need to find our voltage. So we know that our voltage is equal to the current times resistance. And our current is going to be this 16, and our resistance is going to be this 25. So if we multiply this out, we are going to get that our voltage is equal to 400 volts. Now we want to use source transformation again and change this back into a resistor using source transformation. However, we need to combine these two impedances first before we do so. So these are in series. That means we can just add them together. We're going to get a 40 plus J times 30. And now we can rewrite this equation. Redrawing this, we are going to get this diagram. We are going to have our current back in here again. But to find our new current, we are going to have our I equal to voltage over resistance. And we know our voltage to be 400 volts. And our new resistance is this 40 plus J30. So we are going to plug this into here. Now from here, there's a couple different ways we can solve this. The one I'm going to do is convert both of these into the polar equivalent. And to convert to polar, we know that we can use our Vmax, set equal to the square root of our real number squared plus our imaginary number squared. And then to find our angle, we're going to have the tangent -1 of our imaginary number divided by our real number. And if we do this, we are going to get approximately 8 with an angle of -37. Remember, when we do this, we are dividing the numbers and subtracting the denominator of our angle from the numerator of our angle. So this is going to be our current. We are going to have an 8 with an angle of -37 degrees. Now, we found our current, and we can plug this back into our equation. However, our equation wants it in rectangular form. So to put it in rectangular form, we are going to use the formula where we have our number times the parenthesis of the cosine with our angle plus J times the sine of our angle. And now we can plug these in. Plugging these in, we're going to get 6.4 minus a J times 4.8. And we can see that this is the answer for our I of n. Now we need to solve for the Thévenin impedance. And the total impedance is just these two combined together. They are in parallel, so we're going to have to put it in the parallel form, which is 1 divided by our first impedance, and then we're going to have a plus 1 divided by our next impedance, and this is all raised to the -1st power. And from this, we are going to get this equation. From here, we can rewrite it, combining the bottom, and then after we combine the bottom, we are going to convert it into the polar form using these equations right here. That way we can divide it out. And from here, we are going to get these as our polar equations. Now we can divide the numbers and subtract the denominator from the numerator of our angles. And if we do this, we are going to get approximately 56 with an angle of -26 degrees. Now we need to convert this into the rectangular form here so that we may plug it back into our equation. And if we do this for our rectangular form, we are going to get approximately 50 with an angle of -25. And that is how you would go about solving this problem. If you want more network analysis problems, there's a playlist in the description. And if you want notes that go over this material or related material, they will also be below the like button in the description.